Welcome to Understand Chemistry. I am Dr. Bilal, and this is the fifth video in our series on copolymerization. Today, we will explore the QE scheme developed by Alfrey and Price in 1947. But before we get into how it works, we need to understand the problem it solved. Let's start with something you already know: reactivity ratios R1 and R2. They tell us how two monomers will copolymerize, but they are pair specific. Take styrene for example. With methyl methacrylate, R1 is about 0.5, so it copolymerizes almost randomly. With vinyl acetate, R1 is about 55, meaning styrene barely wants to copolymerize. And with acrylonitrile, it's around 0.4. A different story again. So, what does this mean? This means there is no universal reactivity index for a monomer. Its behavior depends entirely on who its partner or comonomer is, and that leads to a real practical challenge. Every time you want to try a new monomer pair, you have to go back to the lab, run experiments, measure R1 and R2. It's time-consuming, expensive, and offer no predictive power. In 1947, Alfrey and Price asked, what if each monomer had its own intrinsic identity? What if we could describe monomers by just two numbers that capture their essential chemical nature? Their solution was the QE scheme. In this model, two fundamental electronic properties of a monomer or its corresponding radical are taken into account. These are resonance stabilization and polarity effects. In the QE scheme, Q represents resonance stabilization that describes how stable the radical is. E represents polarity that describes whether the monomer is electron rich or electron poor. Once you know these two parameters for a monomer, you can predict how it will behave with any other monomer whose Q and E are known without performing any new experiment. So, what did this give us? A shift from pair-specific data to monomer-specific parameters, from purely experimental to genuinely predictive, from an empirical description to a fundamentally insightful model. Now, let's look at how Alfrey and Price built their model. We begin with the four basic reactions in copolymerization. A radical ending in monomer M1 can add another M1, that is self-propagation, with the rate constant K11, or it can add monomer M2, that is the cross-propagation, with rate constant K12. Similarly, a radical ending in M2 can add M2 or M1. Reactivity ratios are then defined in terms of ratio of rate constants. R1 is K11 over K12, that means M1 radical prefer its own monomer M1, and R2 is K22 over K21, that means the M2 radical prefer its own monomer M2. To understand what control these ratios, we look at the rate constants. Take K12 for example. From chemical kinetics, we know it follows the Arrhenius equation as shown here. Here A12 is the collision factor that describes how often the molecule meets with the right orientation, and E12 is the activation energy. Now comes the key insight. Alfrey and Price proposed that the activation energy isn't just one number, it can be split into two chemically meaningful parts. First, resonance effect that describes how much the radical M1 and the monomer M2 are stabilized by conjugation. That's indicated by parameter P1 and Q2. Second, the polar effect. This is the electrostatic interaction between the charge characters of the radical E1 star and the monomer E2. I have explained both of these properties in detail in my previous video. So at constant temperature, we can write E12 over RT is shown here. This decomposition is the heart of the model. It tells us that the copolymerization is not random, it's governed by how much resonance stabilization each species brings and how their polarities interacts. In this equation, P1 is the resonance stabilization of a radical from monomer M1, Q2 is the resonance stabilization of monomer M2, and E1 star is the polarity of the radical from monomer M1 and E2 is the polarity of monomer M2. These four parameters allow us to separate and quantify the resonance and polarity effects influencing copolymerization. Now we are ready to see how the QE equation comes together. We start from the expression for the rate constant K12. By splitting the exponential, we separate the resonance contribution of the radical P1 and the monomer Q2 and the polarity interaction E1 star into E2. We then combine the collision factor and the radical and monomer resonance into a new term P1Q2. Here, if we assume the polarity of the radical is the same as the polarity of its parent monomer, so E1 star becomes simply E1. Now we can write all four rate constants in the same compact form. We can define the reactivity ratio. The radical term P cancels out. For R1 we get Q1 over Q2 times an exponential containing E1 and E2. After simplifying, we arrive at the famous QE equations. R1 equals Q1 over Q2 times the exponential of minus E1 times E1 minus E2. And R2 is similarly Q2 over Q1 times the exponential of minus E2 times E2 minus E1. So what are Q and E? Q captures the resonance stabilization and to some extent steric effects of the monomer. E represents its polar electrostatic character. But note, we have two equations, yet four unknown, Q1, Q2, E1 and E2. To solve this, Alfrey and Price introduced a reference styrene. They arbitrarily assigned styrene Q is equal to 1 and E is equal to minus 0.8. Styrene was chosen as the reference because its radical is moderately reactive and sits near the center of typical monomer behavior. It has a balanced resonance Q and low polarity E, making it a stable baseline for comparison. With that anchor, we can determine Q and E for any other monomer. This table gives us the practical outcome of the QE scheme. Experimentally determines values for common monomers. Here we see the reference styrene at Q is equal to 1 and E is equal to minus 0.8. You can immediately spot trends. Conjugated monomers like butadiene and isoprene have very high Q values, indicating strong resonance stabilization. In contrast, simple monomers like ethylene and vinyl acetate have very low Q values. The E values tells the polarity story. Negative value of electron-rich monomer like styrene and positive value for electron-poor ones. We can notice here that extreme E value for malic anhydride is 3.69. As malic anhydride contain two carbonyl groups directly attached to the double bond. These groups pull electron density away through negative inductive and negative mesomeric effects. This makes the double bond highly electron poor, which pushes the E value strongly positive. As a result of highly electron deficient double bond, malic anhydride reacts preferentially with electron-rich radical. With this table, we can now predict the behavior of any pair just by looking up their Q and E values. Now let's see How we can use these Q and E values to make practical prediction about copolymerization. A common way to visualize this is by plotting monomer on a graph with Q on the x-axis and E on the y-axis. This space is often divided into four quadrants. Quadrant 1 and 2 contain monomers with high Q values. They form stable resonance stabilized radicals. Quadrant 3 and 4 contain monomers with low Q values. Their radicals are much more reactive. This leads to our first rule. Monomers with extremely different Q values do not copolymerize. Well, if one monomer is from a high Q quadrant and the other from a low Q quadrant, their radicals are simply too different in stability. Converting a stable radical into a reactive one or vice versa is energetically very costly. Examples include vinyl chloride with styrene or vinyl acetate with 1,3-butadiene. In these pairs, copolymerization is very difficult. The second rule is the opposite. Monomers from the same quadrant copolymerize more easily. They have similar radical stabilities, so the propagation steps are more balanced. Examples are styrene with butadiene. Both have high Q values and are electron rich. Acrylonitrile with methyl acrylate. Both have moderate Q and similar polarity. But the most famous prediction of the QE scheme is for alternating copolymers. These form most readily when two monomers have similar Q values but very different E values. The strong polar attraction between an electron-rich and an electron-poor monomer drives a regular alternating sequence. This often happens when one monomer comes from quadrant 1 and the other comes from quadrant 2. This map is a powerful design tool. It let us quickly judge which monomer will work together and what kind of copolymer to expect. So let us talk about limitation of QE scheme. First, while it's excellent for qualitative trends, the scheme often fails quantitatively. It is not reliable for predicting the exact reactivity ratio of a brand new monomer pair. You would not use it for precise engineering calculation. Second, the parameters themselves are not universal, and monomers Q and E values are not constant. Third, the model oversimplifies reality in two significant ways. It completely neglects the static effect, the size and the shape of the monomer, and it makes the strong assumption that radical has the same polarity as the parent monomer, which is not always chemically sound. Finally, the scheme output is only as good as its input. Since Q and E are derived from experimental R values, any error or scatter in that original data backed into the parameters, limiting their precision. So, what is the final conclusion? The QE scheme is a brilliant, enduring concept. It provides a powerful qualitative and semi-quantitative guide for thinking about monomer reactivity, explaining trends, and making initial prediction. For any further question or clarification, please consider the comment box. Thanks for watching. We can write E12 over RT is equal to